Alright, good. Now we have phase diagram, and we said it's literally a plot. We said it is a plot between what and what? We said it is a plot between pressure and temperature. So I'm going to be using two phase diagrams here to explain something. What are the two phase diagrams? So I'm going to be using the phase diagram of water and carbon dioxide. These are the two compounds they usually use in JUPEB. Why? Because these are the two that have the different presentation that you want to study in terms of phase change. You understand? There is a difference between the phase diagram of carbon dioxide and the phase diagram of water, and other substances fall into either of the two. That's what we're trying to say. So once you understand these two, you are good to go. Now, let's take for instance now that we have for instance we have a phase diagram that looks like this. Notice this went this way, this guy went this way, and then this guy went this way. Good. In fact, this place here, I'm going to use dotted line and I'll tell you why. Because you won't know where you are crossing this particular boundary. I'll explain to you. Let me extend this line. These are things you have to know. Let's say this is temperature in Kelvin. You understand? If you like stress, you can use other temperature scale, maybe Rankine, depending on how you like stress. So this one now is pressure. These are just kidding. You use Kelvin because that's what they're going to use and ask you. Kelvin or degree Celsius. And conversion from Kelvin and degree Celsius is not supposed to be a problem. It's just addition of 273, right? To convert it to Kelvin. Alright, pressure. I'm going to be using ATM for my pressure. ATM. Now, this one here, this is where the difference is. The difference is in this line. The difference is in this line. You can see this line here went positive slope. The positive slope is a slope that is going like this. If it's a negative slope, it will go like this. This one went positive slope. Yeah, I know you don't know what this line is yet. I will tell you. Don't worry. Just relax. Let's go into the other side. This one now is the phase diagram of carbon dioxide. Phase diagram of CO2. Sharp. Okay. Yeah. This guy owns like this. This guy owns like this. Right? Yes. And I have this. You see that? This other one came like this. Right? In fact, let me just tell you what this line is. The difference is in the interconversion line of fusion. Are you getting me now? It's in the interconversion line of fusion. Because this region here, where these lines have as boundary to, is solid. This is solid region. This is also solid region. But if you look at it, this place here, this liquid, this other place I'm going to do here is liquid. If you look at it here, the line in between solid and liquid is called the interconversion line of fusion. Why? Because fusion has to do with interconversion between solid and liquids. So that line has a positive gradient for carbon dioxide, but has a negative gradient or negative slope for what? For water. This is what I'm doing. So from here now, you now have this like this as usual, and the remaining things fit into place. Or rather use colors to identify my important points. Sorry. These are important points, or rather use colors to identify that. Alright, good. So this guy here, the phase diagram, is representing the phase diagram of water. Now let's identify our regions. I think there are three things you want to identify: regions, points, lines. Now the regions first. This region here, this first region here, is your liquid region. In fact, if you are a smart person, sorry, I said liquid, it's your solid region. If you are following me carefully, you already know that, oh, that means liquid and solids usually exist at lower temperature and probably higher pressure. You understand? Low temperature favors solid, right? That's why you find out that your ice, you don't see ice to be existing at high temperatures. Ice will exist at lower temperatures, right? Good. So lower temperatures, and also we want high pressure for you to be a solid. Why? Because when you have high pressure, your solid, your intermolecular your molecules will be coming closer to themselves. You get? So pressure wants to bring molecules together. Now that's one of the characteristics of solid: compactness, which contributes to their density. But don't be deceived. You know that there's this ideology many people have that solid have higher densities. It's not for all substances. And this phase diagram will show you a review such to you. Just follow me. You have your solid here. You have solid also here. Yes. So at lower temperatures, solids. See, lower temperature, solid. Everything from this line here, everything that's around here like this is solid. Solid. But this one here, you see, solid even for water, solid even have restrictions. Like solid doesn't even want to cross this temperature. Whatever this temperature was, I'll tell you very soon. Whatever this temperature was, beyond it is where water will be solid. You understand? Not like this one here that this temperature here is still crossed, so you can still be solid. You are still solid here at a much higher temperature. You are still solid here at a much higher temperature. So that you must also be at a higher what? Pressure. Okay, very good. Now, this is your liquid. What does that tell you? That below this pressure, you cannot find water existing as a liquid. So you need to know what these places represent. These are magical places. Then we'll get the liquid, and this is our liquid here. Yes. So in this place here now, you have your what? Gas. You have your gas. You have your gas and those places. Gas. You have your gas. So you can see two things support gaseous systems. What are the two things? Low pressure. You can see gas is here, where pressure is low. Low pressure. Why? Because when there is low pressure, molecules are more free to move. High pressure can bring them closer to themselves. Low pressure spreads them out. You get? So low pressure favors gaseous states. Low pressure favors gaseous states. Are you getting that now? Very good. And what? And your temperature. As the temperature is increasing, you're still having what they call it. You're still having your phase to be in gaseous state. But you can see that even at this low temperature here, it's still gaseous. Why? Because pressure was very low. So pressure is what has higher effect on maintaining gaseous phase than temperature. That's what I'm going to. Good. Here you have a state that we call, it's not a real state, that's why it's imaginary line. It's not a real state. Instead, it is a conditioned state that occurs as a result of boundaries. Like this point here, I'll tell you what this point is very soon. Whenever this point is exceeded, that is when you enter into that kind of state. And that state is where you can no longer differentiate between liquid and gas. You look at the substance behaving both as a liquid and as a gas. You can quickly pick out properties of a liquid and a gas from that substance, and that's what we call CSF. So I said CSF, SCF. So what's SCF, right? SCF is your super critical fluid. Your super critical fluid. And I've told you what the supercritical fluid is, right? Supercritical fluid is one in which liquid and gaseous phase shows, I did not say coexist. They are not coexisting. Coexisting means you can see the liquid, you can see the solid, but they are existing in equilibrium. Just like when I have ice inside water, that's coexisting, right? This one here is liquid and gaseous phase shows no differences. So you look at them, the liquid and solid, they are now behaving as that state is showing both characteristics of liquid and solid. That's what we're trying, and liquid and gas. That's what we're trying to say. That's a supercritical fluid. You know, a fluid is anything that can flow. Liquid can flow, gases also can flow. So that point where the differentiating factor of liquid and gas, which is their what? Compressibility is off. Then you see that the thing becomes a supercritical fluid. Alright, very, very good. So let's now come in. We're done with regions. Let's now come into lines. So what does this line here represent? This line separates what? If you are here with me, this line separates solids from gas. See, solid from gas. So this line here is our what? This is our sublimation line. sublimation line. I know when you're in secondary school, you just enjoy that triangular thing. That was what you liked, norms. So you got gas. You have to be able to represent those things on the phase diagram. So you need to be able to know where they exist in. So this one here is the what? Interconversional line of fusion. Now fusion is either melting or freezing. Don't worry, melting or freezing, you consider them the same here. So interconversional line of fusion. So this sublimation here, it means that under these conditions, any point of temperature across this point here, any point of temperature, all these points here, temperature at this point and pressure at this point, can allow that material move from where? From a solid state to a gaseous state. Do you get that now? And if you want to get your fittings right, you can easily just do this. See something. I want to this point here. I've not told you what this point is, but let's just this point. I can just do like this. I can also do like this. Right? I can also do like this. So you agree with me that once your pressure is low, right? Once you have low pressure that is lower than this critical point and temperature that is greater than any point along here, that means once your temperature is like along these regions, it means that that material can sublime from solid to gas. That's what we're trying to see. So any point along this place, any pressure point along here, that can touch these lines, I get to this point, can sublime. That's the thing. So any pressure that is within the sublimation line, or temperature within the sublimation line, allows that substance to be able to sublime, go from solid to gaseous state directly. So this is for fusion, right? The same thing is happening here, fusion. So liquid to gas, that means this is your what? This is your line of vaporization. The line of vaporization and what? And condensation. Very, very important. And this is not the line. That's why I'm not labeling it. Very, very good. The same thing is happening here. This is your sublimation. This one here is your fusion. This is your vaporization. No labeling on that. Alright, very good. So we've been able to identify the lines. Now let's go for the points. There are two major points in your phase diagram. Two major points exist in your phase diagram. Two major points. And what are the two major points? You have your critical points, and you have your triple points. Now look at something. These are three states of matter: liquid, solid, liquid, and gas. You agree with that this is where the three states of matter kind of coexist. I get you now. They coexist here at equilibrium, and that's your triple point. So we'll call this place triple point. And this place here is your critical point. Beyond this point, a liquid and a gas will now share similarities. The substance will start exhibiting both characteristics of both the liquid and the gas at equilibrium, and that is your critical point. Above this point, the liquid or the gas starts behaving as a supercritical fluid. So that's it, very, very simple. So those are the two major points we have. So we have CP triple points and CP critical points. So each of these points have their pressure and temperature. So that is critical point, we have something we call TC and PC. And triple point, we also have something we call TT and PT. So this is the temperature at critical point, pressure at critical point, temperature at triple point, pressure at triple point. Let's go and identify those temperatures and pressure from there. So here we have, this is where we have the pressure at triple points. You can see these are triple points. Trace it to the pressure line axis. So this is pressure at triple points. Trace this one down from the triple points down. This is temperature at that triple point. Let's come here. Critical point is because I just drew it to that this guy is usually high, like noticeably very higher. So we'll just trace it there. So this guy here is your pressure at critical point. This one here is your temperature at critical point. So for this guy here, let's do the same thing here. For this guy here, trace it down. You have your what? Your pressure. Remember I told you pressure is here, temperature is here. So this is your pressure at which point? Triple point. And this is the temperature at triple point. Here you will trace this down here. You have your what? Your pressure at critical point, and then you have what now? You have your temperature at critical point. Good. Now, what's this critical point? If you want to define, or let's have a triple point. If you want to define triple point, you have to make mention of temperature and pressure. So the triple point is that point at which the temperature and pressure, either now, at which the temperature and pressure causes the three states of matter to coexist at equilibrium. So if you don't put that statement where we are writing that it is the temperature and pressure, that cause you are just writing nonsense. You can't just come and write that triple point is the point where liquid, solid, and gas of a material exist at equilibrium. No, you have to say it because those points are pressure, temperature referenced points. So you have to state it that way. So you are saying triple point is that point where the temperature and pressure causes the three states of matter to coexist at equilibrium. Very, very key. That's it. The same way you define triple point, that you go for critical point. It's that point of temperature and pressure where the what? Above which, in this case you write what? Above which. So it's that point of temperature, is that point of temperature and pressure above which. So I'm trying to say when you exceed it, it's just like when you are defining critical angle, above which the liquid or gas are undistinguishable. Are you getting me now? And this state where they are undistinguishable is what we call supercritical fluids. So they become supercritical fluids. So basically, that is it about the phase diagram.